second session, we have Dmytro Arinkin, who will tell us about a modern approach to geometric Langlands.
All right, so first, let me remind you what's going on. So X is a Riemann surface. G is a reductive group. I cannot draw that. Anyway, so G is a reductive group. G check is its dual. Yes. I mean, the fact that it has characteristic 0 is what's important, but since I'm drawing pictures, might as well be. So then the key objects are this. There are two sides. So this would be the A side, I guess. So bund Gx is the stack of G bundles on X. And the other side, the B side, is the space stack of local systems for the Langlands dual group. And more precisely, we want to consider D modules on G bundles. So to say automorphic D modules and quasi-coherent sheaves on local systems. And the naive idea, the geometric, or if you like, categorical Langlands conjecture, let me just write, is that these two categories should be equivalent. And of course, this is not saying much unless you also specify what you want from this equivalence. And I said a few of these required, so a few of these properties were discussed last time. All right. And so today I plan to explain first why I dared put naive here. So this is, this is a pretty clever idea. This is very nice, but still there's something very slightly wrong with it. Roughly speaking, it's like we are trying to construct a Fourier transform and we slightly missed the classes of functions. Somehow the classes of functions on two sides don't quite match. So first I want to explain how we know that they don't match, and then what can be done to fix this. And by the way, everything is derived. So when I say D modules, that means the derived category of D modules. No holonomicity conditions if you care about this, and so anything like that. On the other side, it's quasi-coherent sheaves, again, derived category of quasi-coherent sheaves. Okay, so let's start. So first, what's wrong with this? So what are the problems? And just to put it in a few words, the problem is that the right side is too small. Now, the easiest way to describe it is to use some formalism from category theory. So namely, I want to look at compact objects. So let's see kind of useful definition in general. So I'll give it in the following situation. So let's suppose that C is a triangulated category with infinite direct sums. I'll just say with direct sums, we all know they have finite direct sums, so this just means infinite. And so then we say that an object in this category is compact if home from it respects infinite direct sums. In other words, there is always a map from, so if you have a bunch of test objects that you are trying to map into, So there is always a map from in this direction. So if you have a collection of maps of M into Ni, you can map M into the direct sum of Ni. And the condition is that this map is required to be an isomorphism. Now, the statement is non-trivial only, I mean, the condition is non-vacuous only if the family is infinite. So in other words, then on the left-hand side, you're only allowed to consider M is only mapped into finitely many Ni's. And so what this condition basically says is that a map from M into a direct sum actually must land in a finite direct sum only. So M is only allowed to hit finitely many direct sums. So, for example, if we were just looking at modules of a submarine, this would be equivalent to saying that M is finitely generated. If M is finitely generated, these generators will land in finitely many summons only, and the rest will not matter. If M is infinitely generated, this would fail. So, of course, modules, well, if you just look at modules as an abelian category, that's technically not an example for this definition because I'm looking at the triangulated world. So let me give some examples, some triangulated examples. So, so the two most relevant to me are the category. So I want to look at the categories of quasi-coherent sheaves and categories of D-modules. So first, let's suppose that S is some reasonable scheme. Where reasonable means something, for instance, something like quasi-compact, semi-separated, anyway, some quite weak conditions, or a reasonable stack. Again, if you care about these things, we do. Then you can look at this unbounded derived category of S. It has infinite direct sums, which is actually the reason why I'm working with quasi-coherent sheaves and the reason why I want the category to be unbounded. Otherwise, it will not fall within the scope of this definition. And then compact objects in this category are exactly what is called perfect complexes. In other words, it's a bounded complex of, it's bounded coherent complex, so it has bounded cohomology, they are all coherent, and moreover, it has finite Tor dimension. So it's in, let me write it like formally, it's in dB Koch and finite Tor dimension. Or equivalently, this means that locally on S, it admits a finite resolution by locally free modules of finite rank. Has a finite resolution by finite free sets and modules. Finite rank free modules. Okay. So and again, it's kind of easy to believe that if you believe that that compactness is some kind of version of notion of finite generatedness, and then we're saying that this is some kind of derived version of finite generatedness, that you want to have locally you have finitely many generators, finitely many relations, relations between relations, and so on, but you want to stop at some point. You don't want this to proceed indefinitely. All right, so this is what happens on one side of this geometric Langlands correspondence. On the other side, we have to look at D modules, and the situation is mostly similar. So let's suppose that S is, for now, let me even assume that it's smooth. So suppose S is a smooth variety, so that I don't have to think about definition of D module. Then the situation is exactly similar. That is to say, an object in the category of the derived category of D modules is going to be compact if and only if it is perfect, which means, again, well, you can say the same words if locally has a finite resolution by finite free D modules. Fortunately, well, since I'm assuming that S is smooth, I want to say that basically anything finitely generated will have such a resolution. So this is equivalent to saying that it's a complex of D modules with bounded coherent cohomology. So this is the same as dB coh of D modules. So anyway, so this is the second example. Now, it doesn't quite fit the left-hand side of the geometric Langlands conjecture because some bundles have automorphisms. So this is a smooth stack, not really a variety. And it turns out that this, you have to be careful. So this statement does not literally extend to stacks. So maybe I should call it 2 prime. I don't want to go too deep into it, but let me just say that if S is a smooth stack, then compact objects in the category of D modules can still be explicitly described. But it's not just that. You need to impose some extra conditions. So not all perfect complexes of D modules are going to be compact. But so basically, you have to be careful at points that have non-trivial automorphisms. There, the compactness condition is slightly more restrictive, but it's still possible to write an explicit answer. Okay, now that all this is on the board, I can precisely state what's wrong with this would-be equivalence. Maybe I should put question mark somewhere because it's not supposed to hold. So the problem with this equivalence is that there are objects that are compact on one side, on this, the modular side, but their counterparts on the right-hand side are not compact. And I want to say that this is not just some minor thing, really. This is somehow some fundamental contradiction in the world. That this is like, it's almost maybe slightly dual to the situation if you were trying to write an isomorphism between two vector spaces, and something that's linearly independent on one side turns out to be linearly dependent on the other. So this is pretty bad. Now, let me actually be more precise. What happens? So precisely, you start on the demodular side with a compact object that you know from here. Then some compatibility things tell you what to expect on the right-hand side. And on the right-hand side, this part holds. So you get some complex that's coherent, but this part fails. It has infinite Tor dimensions. So you don't get a perfect complex, only a coherent complex. And I'll I'll describe this more precisely in a moment. But for now, this is just. So I think I at least told you what makes. One thing that makes me unhappy about this would be equivalence. Now, how do we know? So let me say a few words about where this evidence comes from. And again, this will be somewhat sketchy, just like the rest of the talks. So evidence for this, of failure of this naive, of inconsistency, if you like, of this naive statement. Now, I will look at two different ways to see what's wrong. Hopefully, at least one of them will be convincing. So one of them concerns this parabolic induction that I didn't actually say much about, so I'll call it Eisenstein series construction. So this is a really powerful tool if you actually want to do something with the geometric Langlands conjecture. It's for instance, if you're trying to prove something, you actually need to know what this is. So the only reason I didn't say anything about it is lack of time. But let me at least formally say that it relates the correspondence for a reductive group G to the geometric Langlands correspondence for a Levy subgroup. So let's say L in G is a Levy. Then we can define Eisenstein inductor, Eisenstein functors, Eisenstein series functors from D modules, from automorphic D modules for L to automorphic D modules for G. And also we can define their counterparts on the Galois side of the geometric Langlands. So and the compatibility, this functor is supposed to be compatible with the geometric Langlands conjecture. So if the geometric Langlands conjecture held in its naive form, we would have this sort of diagram. And the problem, however, is that the top arrow here preserves compact objects, while the bottom arrow does not. And again, this is something very fundamental. So if we just look at the structure of these two categories and the functor that relates them, and in one case this functor has certain fundamental property, in the other case it doesn't have this fundamental property. And so maybe I should call this, maybe I'll call this automorphic Eisenstein and Galois Eisenstein. And so to summarize, so the problem is that this Eisenstein A preserves compactness while Eisenstein G preserves coherence but does not keep this finite Tor dimension. So it preserves coherence but not compactness or perfection, whatever. All right, so this is what the problem looks like from point of view of the Eisenstein series functors. So roughly speaking, we, maybe in down-to-earth terms, we have certain nice automorphic D modules, which should be called Eisenstein series D modules. Say we can choose this levy to be a torus, then it will be closer to what we usually understand by classical Eisenstein series. Then we guessed what we have this compatibility that tells us what kind of quasi-coherent sheaves they should correspond to, so how they are supposed to decompose into eigenmodules, if you like. But unfortunately, Eisenstein series have certain property, and their image on the other side does not. So this is one way to see that something is wrong with the naive statement. Another way, let me also sketch it, is a certain unpublished calculation of the Reinfelds. So, which is done when the group is GL2 and the genus of X is high. So, definitely, I think greater than 1 is okay. So, namely, what Drinfeld did, he computed in maybe not completely explicit form, but explicit enough for our purposes. He computed this universal Hecke eigensheaf that's supposed to live on the product of local systems, and these are just rank 2 local systems and rank 2 vector bundles. So, and this guy has a lot of nice properties. So, almost anything you want to ask for, with one exception. It turns out that it's not flat. It's not actually a family in the sense that it's not flat over the base of the family. It's not flat in this parameter space local system. In fact, it's not just not flat. It fails. It's not a finite Tor dimension. So you try actually, so it's a family, but if you actually try setting the parameter to some particular value, you try restricting to a particular point here, you get an infinite complex. It's not, so it doesn't really work like this. So let me write this down. So it turns out it is of infinite Tor dimension over the stack of local systems. And this again leads essentially to the same problem. Now, if you try, remember we wanted this, the relation between this universal Hecke eigensheaf and the would-be equivalence is, roughly speaking, that this is the matrix of this operator. And so if you now try applying this operator, then because of the fact that the matrix has this bad property, the corresponding operator will not preserve compactness. So if you start with something that's compact here, you will get something of infinite Tor dimension on the other side. So for this reason, this leads, again, looking at this, it follows that corresponding functor from D modules to quasi-coherent sheaves messes up compactness. All right. So now to summarize, there's a point behind all this which I was kind of curious if anybody was going to ask, but apparently everybody understands this. So somehow the root of all evil is that the stack of local systems is not smooth. So the real problem is that this LS is not smooth. And this is why this this is why this finite Tor dimension is actually a non-vacuous condition. This is why it's necessary. This is why there is difference between coherence and perfection, and one of them is, well, and that's what gets us in trouble. If coherence and perfection were the same thing, this would disappear. So the problem is this is not smooth. This is why coherence and perfection are different things. And this is maybe more familiar on the level of K theories. So this is also why, which one is which? This is, at least this is one kind of system of notation. So K naught and is, well, the value of K naught is different depending on the position of this of the zero. All right, and so basically experimental evidence, which I tried to outline, suggests the following. So, well, first of all, it suggests that this fails, but it fails somehow in a not very spectacular way. It only fails on somehow where this difference matters. It only fails over the non-smooth locus. And in fact, the easiest way to somehow measure the size of this failure is to look at compact objects only. And then basically here's what happens. So we can look at compact objects. This is what happens from teaching lower level courses. Anyway, this is actually strict inclusion anyways. So there are compact objects in D modules, and if you try figuring out where they're supposed to go, you don't actually hit the perfect, the subcategory of perfect objects. But you definitely land in coherent, inside coherent complexes. When I say coherent, I mean what traditionally would be denoted by dB Koch. So bounded complexes with coherent cohomology. And in fact, if you actually study this, for example, this Eisenstein series construction, or study this example more carefully, you realize that it's somewhere in between. So it actually lands in something that's strictly larger than one of those categories and strictly smaller than the others. So in other words, this is too small, this is too large. We need to know which one is just right. And so basically our goal for the rest of the talk is to somehow fill in this box. So for now, I can put a lot of question marks.
Whatever goes in that box, will it be equivalent to compact objects on the left? Or?
You want it to be equivalent. So for now, you can just, well, if you prove that whatever in this box is equivalent to compact objects on the left, that will prove the geometric Langlands conjecture, because both these categories are compactly generated. So it's, I mean, because somehow of formalism in this categorical world, we have a choice. If you like, you can work with big categories that have infinite direct sums. If you like, you can work with categories of compact objects, and the two things determine each other. Right, but for now, I just want to put something here that will be consistent with the evidence, and then maybe tell you why in what way it's consistent with the evidence. All right, and so this requires. Now, I want to say that this is almost like some kind of, in many ways, what goes on is some kind of functional analysis. So roughly speaking, and traditionally, there's usually the analogy with functional analysis is maybe easier to see on the automorphic side, that somehow when we are dealing with D modules, they are kind of like functions. Now, it turns out we also need to think about the quasi-coherent world, about quasi-coherent sheaves. There's also some choice concerning the kind of objects you are dealing with. And let me also say that if you believe that this is like Fourier transform, then somehow the difficulties that we are dealing with, namely what happens along the non-smooth locus here, wouldn't be too surprising, because one of the properties of the Fourier transform is that what happens at infinity comes back as singularities on the other side. That somehow, if you have something that badly behaved at infinity, on the other side, it's you get singularities in the Fourier transform. So here, this is a smooth stack, but it's not of finite type. It's not quasi-compact. So, now because we cannot impose any stability conditions, so it's gets more and more unstable. And in fact, it's this Eisenstein series things exactly kind of go off into, to the horizon. So they go to infinity, so to say. And so it's not surprising that in order to accommodate for this, we actually have to deal with somehow with singularities of this and with singularities of complexes at those points. Now, let me try to make this precise. So this analytic technique, well, kind of analytic technique, it's not really analysis in the literal sense, is so it's on the Galois side of the geometric Langlands conjecture, and it is provided by this notion of singular support of coherent sheaves and coherent complexes. So there is singular support in, let me just say, dB core of LS. Maybe 4 objects in there. And, well, I'm talking about this stack of local systems because that's what I need. But, in fact, this is something general. It works on any local complete intersection. So this is, and, well, I guess side remark is that this stack is not smooth, but it is a locally complete intersection. So, or on any LCI. And so let me just remind you then, well, what the word singular supports, what they usually refer to, and this was already mentioned in this conference, I think, under the name of microlocal support, same thing. So the point is that if S is smooth, then to a D module, or holonomic D module, I guess, to a holonomic D module on S, you can assign its singular support, characteristic cycle, microlocal support, whatever. I don't really need the cycle, just this. I don't care about multiplicities here. So, so you can assign the something that I can call it singular support, which is a closed conical subset in the cotangent space. It turns out that something very similar is possible for the coherent sheaves with the funny modification that instead of looking at the cotangent space, you have to look at the derived cotangent space, which is the reason you usually don't see this. You kind of don't see this thing immediately. So just purely formally, suppose now S is a local complete intersection, then first there is, well, derived, first derived cotangent space to S. Let me just denote it by this. So it sits over S. It's not a vector bundle in the obvious, in the usual way, because its dimension is not constant. Its rank is not constant. So it looks more like a coherent sheaf rather than a vector bundle. And somehow the point is that at smooth points, there is the cotangent space. There is no derived cotangent space. It's purely degree 0. So in other words, you can say that this guy somehow measures non-smoothness of S. So measures non-smoothness And somehow the reason why I require S to be a local complete intersection is because, well, this is somehow the next best thing after being smooth. And this guarantees that the cotangent complex to S at any point sits in two cohomological degrees, 0 and -1. And so so I'm not interested in the zeroth. This is the next one I'm looking at. OK, and so you have this gadget that measures non-smoothness of a local complete intersection, and then this singular support operation assigns to a coherent sheaf on S, or a complex of coherent sheaves, a closed conical subset in here. So it's singular support of F, which sits inside this shifted cotangent bundle. So roughly speaking, let me try to draw a cartoon, basically. So the picture is maybe something like this. Suppose S is now local complete intersection. Suppose, maybe I need to leave more room. So it's maybe smooth almost everywhere, and then there are some points where it's singular. Then this shifted cotangent bundle will just have 0 section. So this is S. The shifted cotangent bundle sits over S, and it just has it always has the 0 section, and over smooth points, that's it. But over non-smooth points, you will have a larger vector space whose dimension depends on, well, exactly how non-smooth the point is. So this is this line. And now if I have a coherent sheaf, so again, it's hard to draw a coherent sheaf, so I'll just draw its support. So you have something sitting on some locus in S. So this is F. Then its singular support, well, it will always have the 0. Its intersection with the 0 section will just be the usual support. So nothing new here. And at smooth points, that's the only thing it tells you. So nothing changes. But then at singular points, it somehow tells you the directions of it also gives you some directions, or I guess I should call them derived codirections or something like that. Anyway, so you get something like some subset in this derived vector bundle. And what it does, it tells you the failure of F to be perfect. So if F is perfect if and only if the singular support is the 0 section. So in other words, I mean, we already know from this discussion that it's important to distinguish, well, I guess we knew before that it's important to distinguish between coherent and perfect things. It's nice to know if Tor dimension is finite or infinite. So this allows you to do something more. Besides just telling whether the thing fails to be perfect, it somehow tells you in which direction it fails to be perfect. So this is somehow directions of failure of F to be perfect, of F's imperfection. All right. Now, how does this help? This also tells us that we have a way of finding a lot of potential candidates for this box out there. Because there's a lot of ways now, using this technique, to find categories sitting between the categories of perfect complexes and coherent complexes. So because perfect means singular support is in the 0 section, coherent means singular support is anything, but there are lots of other restrictions that you can impose. You can basically choose any conical subset here and only consider sheaves coherent sheaves whose singular support will be in this conical set, and that will give you an answer, some category in between the two. So now, we of course don't want some category, we only need one. So for this, in order to fill in this box, I need to understand what the derived cotangent bundle to this particular LCI stack looks like. So there is certain computation that needs to be done, so that applies specifically to this situation. So I can now erase this part about any local complete intersection and look at this stack in particular. Now, the calculation is sufficiently straightforward, modulo the fact that you need to actually work in an actual definition of this. But once you have it, it turns out that the shifted cotangent bundle to the stack of local systems can be realized as the stack of following pairs. So you look at, I was using L and A, where L is the point in the base, so this picture on S. So L is a local system. And A is an infinitesimal symmetry of this local system. So A is a section, if you like, of G twist of this local system. So, and it has supposed to be horizontal. So for example, if G is GLN, I'm just saying we have a vector bundle with a connection and a horizontal endomorphism of this vector bundle. So now you can see that it kind of looks like this cartoon, that most local systems will probably have I guess for GLN there's always scalar. But aside from that, so let's say I'm in the dealing with SLN or PGLN, this will take care of scalars. So there will be if G is semi-simple, most likely local system will have no endomorphisms. So, and for some of them, the dimension will jump, and you have a vector space. A dimension cannot jump too much because this endomorphism has to be horizontal, so it's actually determined by its value at any point. So the maximal dimension is the dimension of G, which will be achieved, say, over the trivial local system. All right, so now we know where the singular support of coherent sheaves on the Galois side of the geometric Langlands conjecture sits. And in order to, now we need to impose some restrictions. We have to decide which coherent sheaves are going to be allowed on the Galois side of the geometric Langlands correspondence. And the following is an educated guess. So there is a particularly nice conical subset, which is related again to few things that appeared in a few of the talks at this conference. Namely, I can look at the appropriate version of the nilpotent cone. So let me denote by nilp. It's really like, maybe I should call it global nilpotent cone, but that's the only one that appears in this talk, so I'll just call it that. So this, let me denote by nilp the locus of pairs local system infinitesimal symmetry, where this infinitesimal symmetry is required to be nilpotent. And so the candidate, now I can fill in this box, that will require some shuffling though. So this corrected or less naive, I don't know, sophisticated version of the geometric Langlands conjecture is that, let me actually leave the naive version here, is that compact D modules should correspond exactly to coherent sheaves on the stack of local systems whose singular support is restricted. It must fall within this nilpotent cone. So these are, let me call it Koch nilp of local systems, which is just coherent complexes whose singular support falls within this nilp. And somehow, so this at smooth local systems, again, you don't see the difference between this or between perfect complexes or between coherent complexes, anything like that. In fact, this is only the difference between this and perfect complexes, which is what we would have in the naive geometric Langlands conjecture, is only felt at local systems that admit nilpotent endomorphisms. So roughly speaking, what happens is that maybe this is the picture of the stack of local systems. Maybe there are some other singularities here. So maybe so you have this, maybe there's low dimension somewhere, then high dimension, or maybe the same dimension. Anyway, so you have this kind of generalized vector bundle whose fiber is just measures and infinitesimal symmetries of the local system. Now, it could happen that at some points there are infinitesimal symmetries, but there are no nilpotent infinitesimal symmetries. So you have something like semi-simple things only. And at those points, you are still constraining the singular support to be in the zero section. In other words, at this point, you still demand imperfection. So it's only at points where there is something nilpotent going on that you sort of relax your standards a little bit. So you say, it's OK, you can be imperfect, but only that way. So you still have to watch your step this way. OK, so this is, now it's hard to make the next comment precise, but it's very tempting to make, at least in some form. So I want to say that informally somehow we are saying that on the Galois side of the geometric Langlands conjecture, we need some more parameters that are somehow of homological nature, but let's ignore this for a moment. I just want to point out that these parameters, so these parameters are like nilpotent symmetries, nilpotent infinitesimal symmetries of local systems. And I want to say that this is very similar to Arthur parameters, so that this is, you can think of this as nilpotent part of the SL2 on the the representation of the fundamental group, so that you have a representation of the fundamental group and the commuting nilpotent operator. So, and hopefully this is not an accident, so it doesn't, it's just too nice to be an accident. Now, let me also make a precise statement. For now, it was mostly observations and definitions, even vague definitions. So here's and this is just one of the consistency checks that we put this kind of this version of the geometric Langlands conjecture through. So, namely, I want to say, so I'm basically trying to explain in what sense this category is just right. And the claim is that it's somehow, that our problem, well, at least problems with the naive formulation was that it wasn't compatible with the Eisenstein series functors. And now I claim that this category is, in fact, it's first of all, it is compatible with the Eisenstein series functors. And in fact, it's somehow the smallest possible category with this property. So the following theorem which is in the paper by myself and Dennis Gatesbury, is that is a compatibility condition. So this Koch-Nilp is somehow, let me put it, the smallest triangulated subcategory of Koch that is compatible with Eisenstein series. So what do I mean by this? Well, so there's this was, I think I called it the Galois-Eisenstein series, which is the function coherent sheaves. It preserves coherence, so I might as well consider it on coherent sheaves on local systems for Levy to coherent sheaves for local systems for G. Now, you can consider it on all coherent sheaves, but we are trying to shrink this. And so in the naive geometric Langlands conjecture, we tried to restrict it to perfect complexes, and this didn't work. If I restrict to perfect on the left, and I try restricting to perfect on the right, I miss. The claim is that these coherent guys with nilpotent support are actually exactly the smallest category that contains the image of all Eisenstein series functors for all Levy, including the improper Levy. So it's somehow, it contains, so in other words, I want to say that this is, you're trying to say, what do I need to put on this side? And you say, well, I definitely want perfect guys there. But I also want guys that came by this parabolic induction, by Eisenstein series construction, from perfect guys for all Levies. And so if I put all those, this is somehow their span. This is the smallest category that contains all those. There are other compatibility, nice compatibility conditions. For example, there's a compatibility with the Satake equivalence. In fact, in some cases, you can actually compute both sides. And by some cases, I mean like genus equals 0, which is surprisingly interesting. And so in all these cases, the conjecture holds. So we'll see what happens. Let me just say that for simplicity, I was talking about compact objects here. But as was mentioned earlier, you can actually pass. So the category of compact objects determines the larger category. So if you don't care about, if you don't want to restrict yourself to this kind of versions, DB Koch and its versions, you can actually find an appropriate replacement on the right-hand side. So this will be the category generated, compactly generated by this category of coherent sheaves with nilpotent support. So the keyword is the category of int coherent sheaves. And so let me just put the word somewhere. So if you you need a slightly different flavor of algebraic geometry to accommodate the category of the entire category of D modules. So let me just say geometric Langlands conjecture basically got to where I started this series of talks, so that these D modules supposed to be equivalent to the category that is compactly generated by this category, which so this is like what is called int coherent sheaves, again with nilpotent singular support on the same thing as before. All right, so sorry for running over a little, just wanted to say these words at some point.